Hi folks. So today we're going to be talking about inference for a single sample, and I'm going to start by just cleaning things up like I always do. I'm going to close my sidebar. I'm going to File, Close All Documents. I'm going to clean up my environment, yes, and then maybe I will also clear my console. And so now I'm going to look for the inference single sample prelab.rmd, and maybe I'll turn on that visual editor so that it looks a little nicer. And I'll hide that outline, and now I think I'm ready to go. So we're going to start like we always do by loading the Mosaic package and loading the example dataset that I use every single time, the GSS clean dataset. I'm pretty sure that this chunk is actually going to give an error when we hit the play button. Yep, and that's because I don't have the file path exactly right. So I'm going to delete out everything inside the parentheses here, and then I'm going to put the quotation marks back in and use my tab trick. So hit the tab key, and I actually have a folder called data, hit the tab key on that, and then tab again to get GSS clean. If I hit the play button, there it is. Okay, so today we're talking about inference for the first time, and there's basically two ways to do inference. So one way, which you might have talked about in lecture, is using simulation. So that would be randomization or the bootstrap. And the other way is to use a distributional approximation. So like the normal distribution, the t-distribution, something like that. In the labs, we're going to focus on that second one, the distributional approximation, because it's hard to do the simulation methods in other types of statistical software that get used in the Stat 220 labs. It's really easy to do in R, so if you want to know how to do it in R, let me know. I'm happy to show you, but we're not going to do that in lab. So today's lab is about inference for a single sample, and that means for just one variable. And we're going to do inference for if we have one categorical variable, and inference for if we have one numeric variable. And that means that we're going to do inference for a single proportion, because that's the summary statistic for a categorical variable, and a single mean, because that's one of the really common summary statistics we use for a single quantitative variable. So when we do inference, for example, for a single proportion, we're going to need to use a normal distribution. And when we do inference about the mean, we're going to need to use the t-distribution. And either way, we need a formula for the standard error. So you probably learned these in lecture, but if you're doing a single proportion and you're making a confidence interval, your standard error of p hat is the square root of p hat times 1 minus p hat over n. And if you're going to use the approximation, like use the normal distribution, then you need to make sure that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. If we have a single mean, then our standard error formula for x bar is s, the standard deviation, over the square root of n. And again, there's conditions. We need to ensure that our data is normally distributed, or that n is greater than, or maybe it's greater than or equal to 30. You might want to check the textbook on that. So we're going to start by doing inference for one proportion, and we're going to think about the proportion of people who are self-employed. So we're going to try and find our point estimate, just like our best guess for the proportion. And the way that I would do it is using the tally function. We learned that back in the categorical variables lab. So I'd like to see if you can remember how to find the proportion of people who are self-employed. So maybe pause the video and see if you can do it. Okay, so I'm going to use the tally function, parentheses, and then since I just have one variable, I'm going to start with the tilde. And my variable is self underscore emp underscore or underscore works underscore for underscore somebody. And my data is equal to GSS. And if I just hit the play button on this, I'm going to get the counts, the number of people in each of these categories. But I can change the format equal to proportion and then hit the play button. And now I get the proportion that are in each of these categories. And so it looks like a little bit less than 10% of people are self-employed. If we wanted to do a data visualization, we could make a bar chart. So very similar code, but gf_bar. And then if we hit play, okay, it looks like about, well, it's a little hard to see the percents here because it's the counts, but, a small proportion of people are self-employed. So if we're doing inference, what we want to say is, we observed around 10%, but what other reasonable values we could have observed? So that's a confidence interval. I want to say, I'm confident that the true proportion of people that are self-employed in the United States, not just in our little sample of 2,000 people, the real proportion is between, and then have some numbers. So we could do this by hand. We could use R like a big calculator, and we could do that square root of P, which would be 0.098 times 1 minus P over N, and take, square root that whole thing. Or we can ask R to help us out. So the function that would help us out here is prop.test. And if I run prop.test with the same stuff in the middle, the tilde self-emp or works for somebody, comma data equal GSS, I get some output. And so it says with success equals self-employed. So I think that's actually what we wanted, but let's say that it had picked incorrectly, or we wanted to just be really explicit. We can specify that success should be self-employed. So if I hit the play button here, this is actually going to look just the same, but if I put in someone else, now it's going to say success equals someone else, and all the numbers are going to change. So I'll put it back to self-employed. And then I get a lot of useful stuff in here. I get the 95% confidence interval, which says 0.09 and then 0.116. And then it has the sample estimate, and that's my p hat, and it says 0.1026. And I think the reason why that's a little bit different than the number that we found before is I think that the prop.test is dropping out the NA values. And we could verify that. If we went back up to our tally, I think that I could put in use NA equal, in quotes, no. And now it's doing the proportions without the NA. So self-employed is really around 10%, 0.102, and that's the same P estimate, P hat that we saw here. So we've got our interval, we've got our estimate. If we want to interpret it, the way that I usually interpret these intervals is I am 95% confident that the true proportion of people who are self-employed is between let's just round to 9% and 11.6%. So I'm 95% confident that the true proportion of people who are self-employed is between those two numbers. And does that make sense? Yeah, I think it kind of does. My understanding of, people's work habits is that most people work for someone else, but there's a small proportion who are self-employed.